Hello class, this is Professor Finan, and today's lecture is lecture 2.2, and we're going to cover the Taylor series expansion and polynomial linear regression models. Okay, so first this hopefully is review. Let's review what are Taylor series expansions. For what I'm going to call a general nonlinear function y equals f of some function of x, under the condition that this function f is what I call well-behaved, which means it's infinitely differentiable and continuous. Any general nonlinear function then, meeting these conditions, can be expressed as an infinite sum of terms that are calculated from the values of the function's derivatives and evaluated at a single point A. So this is for the bivariate case. So y equals just function of just one input variable. And so the classic example for Taylor series expansion, you have some point A. So it's the function evaluated at A plus f prime evaluated at A. This is the first order, the first derivative of the function evaluated at x equals A, divided by 1 factorial, times the variable x minus a plus the second derivative of f evaluated at a divided by 2 factorial times x minus a squared. So this is a linear term, this is constant term, linear term, quadratic term. Now we have the third derivative evaluated at a over 3 factorial, then there's a cubic term. And this goes on and on. So this is actually called a power series. This is the sum from n equals 0 to infinity. And here's the formula, f to the nth power evaluated at a, the nth derivative, divided by n factorial times x minus a to the n. And so this x minus a to the n, this is the general form of a polynomial function. And so if a equals 0, and a lot of the textbooks and maybe on the internet, some of the example problems, a lot of times they'll assume a equals 0. That is not always the case. A can be any point in the input space. But if a does equal 0, that's called the Maclaurin series. And so that's the bivariate case. We'll go to the multivariate case in a second. So why do we use Taylor series? And so this has some practical significance. So one is Taylor series can represent a complicated functions as relatively simple polynomial functions. And so polynomial functions can be easily and efficiently evaluated by computers and calculators. And also many times in science and engineering, we have to perform integrals. It's very easy, and there are analytical integrals of the polynomial functions. It's very, very easy and fast to do. And also, the Taylor series requires local derivative information. And so, with computers, these local derivatives about a point can be evaluated numerically from data, okay, using the finite difference method. Especially if you're using a computer simulation code to generate your data set, it's very easy to calculate the derivative information numerically. Yes, and this goes back to also, we talked about in parametric regression, you as the analyst, we have to assume a functional form of our regression model. And so if you don't know the functional form or you don't have any information about the underlying physics, we have to then estimate the function of x from a data set. And so if f is unknown, we know that if it's differential and continuous, this is the representation. So especially these low order polynomial terms are the leading terms in the Taylor series expansion. Yeah, and so if you don't know the functional form of that, the functional form, you can use the finite differencing methods to evaluate derivatives. And this is actually something called the form and SORM methodologies, which are used for response surfaces and also for the limit surfaces. This is called first order reliability method and second order reliability method. And so these Taylor series are a foundation of many regression methods. And this is especially if you're interested in the function in a finite range of predictor values in the vicinity of A. And so especially if you're sort of looking at a localized subspace, low order polynomials tend to work well because it's actually, it's sort of, it's given that these general nonlinear functions can be expressed as polynomial functions. But also words of caution about the Taylor series. And so the true functional form is the infinite sum. But usually in practice we have to then truncate the expansion. And so we usually truncate the power series to approximate the function. And so for example, the nth order Taylor series is truncated at the nth derivative. And another thing is higher order Taylor series does not necessarily mean higher accuracy, okay? And so, and for some particular functions, the accuracy can actually decrease if you keep adding these higher order terms, okay? And actually, or the solution might become unstable. It's accurate in one region, but then has a huge error somewhere else. And I'll show a practical example in a few slides later. And so this is where you need to understand what's called truncation error distributions, which are function specific. And so sometimes a low order polynomial is a much better fit than a higher order polynomial. And also one issue is some simple or commonly encountered nonlinear functions require high order approximations for accuracy. And so let's just look at the function sine of x in the next slides. Oh, and this is the Taylor series with multiple, this is the general case with multiple independent variables. And so we can extend the Taylor series to the multivariate case y equals f of x, where the x is the vector of input parameters. And still the point A now it's the point in the multidimensional input space. And so I'm going to call it now the Taylor series expansion. It's equal to the function evaluated at that reference point, plus now it's a summation. I equals 1 to n, and we have n input dimensions. And so this is now the partial derivative of the function with respect to xi, evaluated at the point, times xi minus ai. So that's a summation. Now for the second order derivative terms, 1 over 2 factorial, now it's a double summation over I equals 1 to n, j equals 1 to n. The second order derivative, second order partial derivative. And here it's xi, the partial derivative with respect to xi times the partial derivative with respect to xj. And now it's xi minus ai times xj minus aj. And so this is where, remember in our previous lecture, we talked about the interaction terms. x1 times x2. I think we had beta, I think it was beta 5. And so here you can start getting those interaction terms, okay? And then and this extends to the higher order derivatives and polynomials. Here it's a summation over 3 variables, third order derivative, but partial derivative with respect to the xi, xj, xk. And then now, so this is now cubic functions, including interaction terms. And so, and this can go on. And so in vector notation, often we can write this in vector notation, where our Taylor expansion T is f of a plus x minus a transpose. So this is now a row vector. Times d is the gradient operator operated on our function evaluated at a. Gradient is the column vector of the partial order derivatives. The second term is 1 over 2 factorial. Now it's x minus a transpose. This is the Hessian operator, is the Hessian matrix actually. So x minus a is a row vector. column vector. This is the Hessian matrix, and then this is a row vector. And so this involves matrix and vector operation, but it returns a single value. And then there's more for the higher order terms. And this is the general formula. Yes, and so let's go to the next slide to talk about the Jacobian and the Hessian. So the gradient of the f is a vector of the partial derivatives with respect to each input dimension. And then this is the Hessian matrix, which is a symmetric matrix, so the off-diagonal elements are identical. See, okay, so the off-diagonal, it's a symmetric matrix, okay? And so the form and SORM, the first order reliability method and second order reliability methods, second order uses the Hessian matrix. Okay. So words of caution about Taylor series and multivariate applications. And so most engineering applications are multivariate. That's why some of the textbooks and some of the internet resources always doing bivariate case, which is, in many applications, that doesn't give us the information we need. So, for example, design optimization. For example, if you're trying to minimize the drag on an airplane wing, there's what, probably around 10 variables? I actually don't know, I'm not an aerospace engineer. The peak cladding temperature of nuclear fuel during accidents, those are some of the simulation data I showed in the first lecture. So there are dozens to possibly hundreds of variables. And also power peaking factor of a nuclear core, there are tens of thousands of input variables. And this is actually mostly what's called cross-section data. And so the one problem with Taylor series expansion is the number of data points expands geometrically with the order of the expansion. So for example, to calculate the Hessian matrix numerically, you would need 4 times n squared data points, which is basically you need to do that many forward code simulations. So when you have 100 input variables, you would need 100 times 100 is what, 10,000? You would need 40,000 forward computer code calculations just to calculate the Hessian matrix. And there are then other, but usually complicated methods to calculate or to estimate derivatives. This is if you're using a computer model or computer simulations. You can use, for example, there are adjoint methods in reactor physics, but it requires solving the adjoint equations. And also you can even do what's called symbolic derivatives of the equations in the source code using the chain rule. And so there are some third-party softwares called automatic differentiation codes that will generate these symbolic derivatives. They process your source code and they continually apply the quotient rule for differentiation. But you can get these very large, cumbersome derivative equations. And so even if you do this, so if you do have an application of a large number of input variables, even if you do this complicated procedure, so even if you calculate the first, second, and even third order derivatives, the approximation might be still inaccurate for your problem under study. Or it might only be valid in the local region around A. And so even if you do all this work, it doesn't guarantee a good global solution. But if you automate this procedure, you can actually repeat this at different reference points in A's and start to construct at different reference points and see where then the models intersect, kind of as the interpolation between the reference points. And that's actually what the form and SORM methods do. They build it at different reference points and then they try to connect those localized surfaces. Okay, so let's do the quick bivariate example. This is the sine function you should all be familiar with. Obviously the sine of x is a well-behaved function. It's infinitely differentiable, it's continuous, and also it's relatively slowly varying. It's kind of linear, and then it sort of slowly turns over, becomes linear again. Not only is it continuous and infinitely differentiable, it's sort of a slowly varying in this input space. Yeah, and especially at x equals 0, about x equals 0, you can actually approximate it with just a line of best fit, actually. And so let's test what order of Taylor series expansion is an accurate approximation from negative pi to pi. Here's our Taylor series expansion formula, and just to, so students who are watching the video, you should, what is the derivative of sine and what's the derivative of cosine? Okay, and so you should now take a minute, write out each one of these terms. Okay, follow the equation. What are your derivatives of sine of x? So I'll give you a minute or two. So you should work out. I'm actually not going to tell you. You got to get your mind working. And so you can pause the video. So please pause the video and fill in the blanks, okay? And so now let's do the expansion of sine of x. And we're going to do it at two different reference points. So let's do at x equals 0. So a equals 0 in this case. So this is the Maclaurin series. And so sine of x expanded about x equals 0 becomes, it's actually only the odd derivatives, because the derivative of cosine evaluated at 0 is always 0, negative sine of 0. So it becomes now, we have these odd polynomials, this infinite sum. And then here's the actual equation. And so here I've plotted, I've gone beyond the plus or minus pi. The solid blue line is the true sine function, okay? And then for each I have plotted two curves. So the first graph here, the dashed black line, is n equals 3. So we've truncated, we just used the first two terms. And if we look, it's actually a very, very good fit in the linear region. But as soon as we make it to the maximum and minimum, see, the solution is diverging. And actually, the n equals 3, it goes down to positive. If you keep going out, it goes down. This is right around pi, too. It starts to convert. It will go down to negative infinity. And then at negative pi, it's going to positive infinity. And so the n equals 3, it's very, very accurate, but only in that linear region. And now that's probably expected because you have a linear term right here. Now n equals 5, now we're going to the next term, n equals 5. So here, then that's the red line. So here, when we get to around positive pi, it actually it agrees with the peak, the maximum here quite well, but past the peak it diverges, and then it goes back up to negative infinity. Same thing here, it matches the minimum quite well, but then it diverges and then actually inflects and goes down to negative infinity. And so here we got n equals 7, so we truncated the 7th term. We actually now match the linear region, the two peaks, and we start to get good agreement in the second linear regions. But once again, now it extrapolates out to the positive infinity and negative infinity. And n equals 9, we start to capture some of the minimum and maximum within two periods from our expansion point. And so we can keep doing this, n equals 13 and 15. We can see as we increase the order, we start to match as we go out at the longer periods of pi. We can match the function, but always, eventually, the solutions diverge and go to either the positive infinity or negative infinity. And so, depending on the range, you know, the expansions can give very accurate solutions over certain ranges. But also, if you try to do an estimate with a limited expansion, when you've got one of these regions where it's going to positive minus infinity, you can get the completely incorrect answer. And so that's what you have to watch out for. These expansions, these truncated expansions, might only be accurate over a limited range of your predictor value. And so now, let's focus on n equals 3. At the expansion at n equals 0, we have very accuracy in the linear region, but you see how we start to under and over predict we under predict the maximum and then diverge, and we over predict the minimum and diverge. But if we what happens when we shift our reference point? If we choose x or a equals pi over 4, now we're shifting a little bit higher up. And so n equals 3, here we get better agreement with the third order expansion. Oh, and now it's a different, now we have we have more derivative terms as well, because both the derivative cosine and derivative sine at pi over 4 are non-zero. And so we start to we actually have a first order term, a second order, a quadratic term, and the cubic term, fourth order, fifth order. And so by choosing this expansion point, we only have the odd terms. And so at this n equals 3 model, we're truncating here. So we actually have 1, 2, 3, 4 terms. 4 terms. Yeah, and evaluated at 0 is also non-zero. So we have 4 terms in the third order expansion. So here we're actually, and we've shifted our reference up the linear region. So we have much better agreement for this maximum peak, but now we have a divergence. We underestimate the minimum, and then it goes back then to infinity again. And same thing, n equals 5. We're starting to capture this peak, but it goes to positive infinity. Here, we go up, but we have a really overestimate by a factor of maybe 300. It's about 1. It's 1 compared to a little over 3. So we overestimate the maximum by 300%, and then it goes back down to negative infinity. But we can keep, of course, increasing, and we start to get better accuracy over a wider range of the input space. And just to show you some detail, the n equals 9 goes off scale. So if I expand the y-axis, this is n equals, so here in these plots, we're showing the sine function, the true function, evaluated for n equals 3, the third order expansion, a equals 0, third order expansion at pi over 4. So you can see the relative difference between the two expansions. And here at n equals 9, what's interesting, for the pi over 4 case, there's a huge peak here. It goes all the way up to over 45, and then back down to negative infinity. So just to summarize, this is what you need to think about. What is really the size of your input space, and what is the variation of your variables in your data over that input space. And actually, if you wanted, for example, if you wanted an accurate model for all x going from negative infinity to infinity, the sine function is a periodic function. So here, if you use the 0th order model, y equals a constant, beta naught, the mean, this would actually give the accurate result for all x. But you would lose all of the amplitude information, but you would but using any of these other models, now you're going to plus or minus infinity, so you would have huge errors. And so just remember, sometimes a very simple model might give you accuracy but no detail. In this case, we would lose all of your amplitude information. So low order polynomial fits may only be accurate over a limited subspace. All right, that is it for the Taylor series expansion, but this does tell you, like I said, the vast majority of, since the 1800s, most regression models, probably 70 to 80% of all regressions have been linear models, and of those, the vast majority have been these low order polynomial fits. But that really naturally comes out of it's the regression has a closed form analytical solution, but also low order polynomials are the leading terms of Taylor series expansion. And so the Taylor series expansion and polynomial linear parametric models They're closely related. All right, that is it for this lecture.